Hello guys, hope you all are doing well. So in the continuation of the previous GATE series, we have completed 1996 section A, and now we will solve 2 mark question of section 1996. Then we will make a separate video for 5 marks questions. Okay. So very first question here is the ratio. This is the ratio given dxy y x1 to x2 x2 minus x1 upon y at x equal to x2, x2 is greater than x1. So this is the condition where where 1 upon y is a monotonically increasing function of x. The ratio, what is the value of that ratio? Okay. So very first thing, we have that 1 upon y is a monotonically increasing function of x. Let 1 upon x is equal to y. So let's see the graph between. So 1 upon y, whatever the value you will take, the graph will be like this. Okay. So in place of 1 upon y, we will put x square. So now the ratio become this. This ratio will become this. Okay. After integration, we have to solve this only integration, nothing else. Just okay. So we will get this. Now here is x only, but the numerator is at x equal to x2. So we will put x equal to x2. We will get this. Okay. Now take x2 cube common from both sides. So this will and this will cancel out. We will ultimately get this. Now, given that x2 is greater than x1, so x1 by x2 is always less than 1. That is for sure because x2 is greater than x1. So the ratio of x1 and x2 always less than 1. Suppose we have taken this ratio at max 0.99, highest value. It could never be 1. It is always less than 1. So 0.99. So putting the value here, and we will get 0.99 less than 1. So this ratio will always be less than 1. So our answer is always less than unity. Okay. Now the number of boundaries around which material balance can be written are okay. So very first thing, for material balance, one can be written here, second can be written here, third can be written around the reactor, and the 4 material balance will be overall feed product. Okay. So total number will be 4. The number of independent balances that can be made around the reactor, independent, then this will cancel out, because when you will make the balance over the reactor, then input and output will come. Okay. So 1, 2 and 3. 1, 2 and overall 3. Okay. This type of question will not ask nowadays. For an isothermal variable volume, that means variable volume means EA is not 0. Batch reactor. Following relation is applicable for first order irreversible reaction. Let minus RA is equal to KCA for first order reaction. We know that minus dCA by dt is equal to KCA. Okay. CA is equal to CA naught 1 minus XA 1 plus epsilon AXA when EA is not equal to 0. Putting value here, d by dt CA naught 1 minus XA 1 plus epsilon AXA is equal to K CA naught 1 minus XA 1 plus epsilon XA. Okay. So this will become CA naught will come out, 1 will become 0, this will become dXA, minus and minus will become plus upon 1 plus epsilon AXA divided by dt is equal to K Ca naught. This will remain same. 1 minus Xa 1 plus epsilon A Xa. So this will term cancel out. Ca naught and Ca naught will cancel out. So dxa upon 1 minus Xa is equal to K dt. When you will solve this, you will get this. Okay. A rotameter through which air at room temperature and atmospheric pressure is flowing gives a certain reading for a flow rate 100 cc per second. If helium molecular weight 4 is used and the rotameter shows the same reading, the flow rate is. Okay. So very first thing, venturi meter, orifice meter, pitot tube. Okay. These kind of formula is applicable. I don't know what very certainly the formula used in this question, but Q is directly proportional to root 2GH. Q is directly proportional to 2 del P by rho, where rho, this one is flowing fluid rho. Okay. So Q is directly proportional to root del P by rho F, right? Rho of fluid. And rho of fluid, we know that P m upon RT. Put this value. So Q will be directly proportional to root m, root of molecular weight. Okay, so remember this formula. If volumetric flow rate and molecular weight is altering in the question, okay, if the question is changing only molecular weight and asking for the Q, volumetric flow rate, use this formula. So Q1 is equal to M1 Q2 M2. Okay, so Q1 is we have 100, Q2 we have to find. So M1 1.23, molecular weight of air is 28.8 and 4. So Q2 is equal to 100 root 28.8 divided by root 4. So the answer will be 269 cc per second. Let me check once whether I am right or wrong, but I think this is the answer, 269. 100 into 28.8 under root divided by 4 under root, 268.8, 269. Okay, so a bed consists of particle of density 2000 kg per meter cube. If the height of the bed is 1.5 and the porosity is 0.4, the pressure drop required to fluidize bed. In this question, the formula will be used but this fluid density is missing. The question is not specifying which fluid we are using for fluidizing the bed. The particle is there, bed of particle is there, but which fluid we are using to lift the particle up to make the bed fluidize is missing. So next, the sphericity of a cylinder of 1 mm diameter and length 3 mm is, I told you it will be 7-8. I told you in the earlier when we were solving 1991 question, there is a question of sphericity where length equal to diameter. I told you to remember length equal to diameter, length equal to 2 times diameter, length equal to 3 times diameter, length equal to 4 times diameter. I told you there the value of each specific thing. This is L equal to 3D, so 0.78. Okay. And I have told you the procedure how to find a sphericity very clearly, okay, in 1991. So go through that lecture. The hydrodynamic and thermal boundary layer will be merged when we know that P mot, mo is momentum, T is thermal, both are 1 when Prandtl number is 1. Both will merge, okay, means equal. when the ratio of Grashof number to the square of Reynolds number is 1, mixed convention. Okay, learn as it is, no need to go in deep. Okay, the theoretical minimum work required to separate 1 mole of gaseous liquid mixture at 1 atm. The same question GATE has asked in 2021 or 2022. Some a question is there. Okay, so we know that work minimum is equal to minus del G, that is minus RT ln xi minus RT ln xi. Okay, sorry, minus RT summation of xi ln xi. Okay, so minus RT is there, 0.5 ln 0.5 plus 0.5 ln 0.5, so it will minus RT ln 0.5, RT ln 0.5 minus RT ln 0.5, this way. Okay, okay, given 3H2 plus CO that give 3CH4 plus H2O. Kp is this, second reaction Kp is this, and the third reaction. So what is the value of Kp of the third reaction? So very first, see first reaction. What will be the Kp of the first reaction? It will be H2O CH4, no stoichiometric coefficient is there, CO H2 cube. First reaction Kp2 will be CH4 H2O square and CO2 H2 to the power 4. If I divide both of these two, okay, and then like this, I will write Kp1 divided by Kp2. So what is the value? H2O CH4 CO H2 cube. This becomes CH4 H2O square CO2 H to the power 4. So let's see what will cancel out. H2O remain, CH4 CO H2 will remain. So see, third reaction is CO2 plus H2 upon CO and H2O. So divide both the things. What? 10 to the power minus 1.84 divided by 10 to the power 1.17. You will get this. Okay. Now, the rate expression for heterogeneous catalytic reaction is given by. This is very important question. Sometime it is asked, what is the rate controlling step? We will see a question after that. So this type of question is very important because GATE has continuously asking this question in 2000 as well, 2003 as well, 2004 I think, and some other exams as well. So we will discuss I will make a complete lecture on this particular thing because it is important concept. Okay, and there are few points to remember before going to the exam. So I'll make a separate video. It will hardly take 10 to 15 minutes, okay, to understand this topic. So but right now we will solve this question here, but for a clear understanding I will make a separate video on this particular topic, that is very important topic. So we have that minus Ra is equal to, we have to find the overall activation energy, right? I think so. Apparent activation energy. EA is equal to the activation energy of the reaction. So the rate expression for a heterogeneous catalytic reaction given by this, where K is the surface area constant, K adsorption. If KR and PR is greater than this particular thing, uh, the apparent activation energy EA is equal to, okay, apparent activation energy we have to find. Okay, so we have very first K, KA, PA 1 plus KA, PA, KR, PR. Okay, so we have this condition that this KR, PR is greater than this one. Okay, so this will become 0. K, KA, PA upon KR, PR. Okay, now write everything K naught e की power minus E upon RT. Okay, into K naught e की power minus HA upon RT, K naught e की power minus HR upon RT, delta HA, delta HR. Okay, now you will get this answer after solving. Okay, so yeah, this particular question we will not see right now because some of the information is missing, and I will make a certain separate video for that question. Okay, when an exothermic reversible reaction is conducted adiabatically, a rate of reaction, very first reversible exothermic, that means an optimum temperature is required, and adiabatically, suppose this is the reactor and we have closed it everywhere so that no heat and no heat will come in and go out, but there will be a certain energy required to run the reaction, that is called the optimum temperature. So the reaction is taking place, and reversible exothermic reaction. Okay, so the rate of reaction will be at T equal to 0, it will increase, it will convert it, because for reversible adiabatic we have to give an optimum temperature and high pressure. Le Chatelier principle will apply, high pressure if the moles is decreasing. Okay, now minus RA at T is at some time, minus RA at T equal to infinite. So at some time it will go to its maximum value where it will form B. Now overheating will dissociate because optimum temperature is required. If we increase the temperature above the optimum temperature, the dissociation of B takes place. So it will passes through a maximum. Rate of the reaction passes through a maximum. Okay. You will understand this question after reading Le Chatelier principle, what it is saying. Okay. Or go through the example of ammonia production. Okay. A typical exothermic irreversible reaction conducting high pressure industry, dehydration of ethanol. Transfer function of ideal proportional plus reset controller. See, reset controller, that is reset time, we denoted as TR, is reciprocal of integral time. Always remember, reset time is reciprocal of integral time. There is a line in Kuffner, Donald R. Kuffner. There is a line. After you will read integral controller in that book, then there is a line that reset controller is reciprocal of integral controller. Okay, so so this will be the answer, because Kc 1 plus tau is, then Kc 1 plus 1 upon Ts. Sorry. Okay. An example of orthothermal reaction, ethylene oxidation. In a mixture of benzene vapor and nitrogen gas at total pressure of 900 mmHg. 900 mmHg is the total pressure. If the absolute humidity of benzene is 0.2 kg benzene kg nitrogen, the partial pressure of benzene in mmHg. So we know that H is equal to Pa upon P minus Pa. Okay, into M benzene divided by M nitrogen, right? So 0.2 is equal to Pa P minus Pa into 78 upon 28. Okay, so when you solve from here, you will get Pa is equal to 60.28 mmHg. Okay, 60.3. Okay, so if you have any kind of confusion, anything in the 2 marks question, just comment it below. And the question which I have left, I will make a video because that part is very important. So bye guys, take care.